Hi there, this is Matt Heffernan. Welcome back to my channel. We got another episode here of Slithy Vlogs, again, dealing with the 8-bit Battle Royale, but a little bit of an offshoot from that. I previously did a video about the Commander X16, sort of going off in the direction of, well, what can that machine actually do? And that led to comparing it directly to the Sinclair ZX Spectrum Next and the Mega 65. And what I mainly learned in those comparisons was that the Commander X16, while pretty impressive in its own right, is not quite as powerful as its competition in the modern 8-bit retro scene. These other machines are not tied to using actual CPUs that are coming out of the 8-bit era, where the Commander X16 is using a real 6.5 CO2, an actual discrete chip, once that goes into production. The other machines are actually doing FPGA implementations of 6502 and Z80 based processors with additional features built into them and running faster than those legacy chips. Like if you bought a modern 6502 or a modern Z80, these machines will actually run those chips faster than the modern discrete CPUs. So it's definitely a different class of machine. And also, the other really big thing I learned was how little I understood about how both the Mega 65 and the Spectrum Next actually work. And so today we're going to take a closer look at the Spectrum Next. I got a lot of good feedback from the Spectrum Next community, and I'm going to share some of the results that I got from that. So first of all, let's take a more in-depth look at how the Spectrum Next handles its video. Now, like the classic Sinclair ZX Spectrum, going back to the original 16 and 48K models, it has an implementation of the uncommitted logic array, or ULA. And with that, you can completely mimic just exactly how the legacy ULA worked in what it calls the Spectrum video mode. So you get all the standard hallmarks there, the 256 by 192 bitmap with the 8 by 8 color blocks, where you can have a paper color and an ink color out of this 16 color palette, in which two of those colors are black. So basically 15 colors, and in each 8 by 8 block you can only have one of those colors for foreground pixels, and and another one of those colors for the background. And that gets you that very easily recognizable spectrum type graphics because of the side effect or perhaps intended effect called color clash, where you can't get more than two colors within those 8 by 8 boxes. So the Spectrum Next takes a few different approaches to sort of get around that limitation and still preserve this backward compatibility with the legacy machine. So the ULA for the Next is what's called an enhanced ULA. And within that enhanced ULA, there are additional video modes that are available. And these are all based on the later Spectrum models, both the American version and some of the later ones that you would see from Sinclair and Amstrad eventually, and sort of just try to bring in some of those additional capabilities to try to mimic, maybe not perfectly, but getting a similar level of capability for the Next. So, for instance, there's a double buffering mode, so you can effectively double the screen RAM space, so you could have 2-bit maps in memory and switch between them to have smoother animation, which is pretty standard for modern graphics. Once video RAM became a lot cheaper, it became very common to do double buffering. And sometimes it's just done in regular RAM, but it's just a very common thing, so that you're doing all of your changes to one version of the screen bitmap and still displaying the other one. And then once you're done rendering this other one, at that frame change, you can then just switch them out rather than seeing those changes happening and getting some different tearing effects and other just unpleasant artifacts that you can get from single buffering. Including flashing, and that can upset folks with epilepsy, and you want to have a smoother looking game. And so then there's some others. There's a high res mode where you still have those same character sized color blocks, but you get twice the horizontal resolution. And then there is that's called the high res mode. Then there's the high color mode, so it's the same resolution. That's still the same 256 by 192, but then instead of having 8 by 8 color blocks, you have 8 by 1 color blocks. So now it's where before that color clash area was that, say, whole character size, now it's just one row of pixels in that character. It has to be those two colors. So you can get a lot more colors on the screen, but you're still very much limited in terms of not being able to have independent pixel coloring. And you'll still have color clash, you'll just have a more finely detailed color clash. And then we get to the mode that last time I thought, hey, that's the winner. This is what I'm going to use, the low res mode. So it brings resolution down to 128 by 96, but it gives you a full 256 color palette to work with. And so that's what I used to create a fractal, because seeing some of the other things that the Spectrum had, so beyond the ULA, it has what it calls layer 2, and then there's a tile map you can have, and there's sprites. So all these new things are added. And in my naivete, I thought layer 2 was just another ULA layer. So you could have kind of like the Commander X16, where you have 2 layers to work with, and the second layer can be just like the first layer. You can configure them the same way, with whatever you have video RAM for. And the thing with the next is you have a lot of RAM available to you, and this fairly complex banking type configuration, and it lets you do a lot of different things to really be able to very flexibly swap in and swap out in different segments of the RAM. And within the memory map, it's very complicated. Eventually, I'll make a video on how all that works. But suffice it to say, because of that, I just assumed layer 2 was just another one like that. And I have learned that, in fact, it is something quite a bit different. And we're going to get into that real soon. But for now, the main thing to understand with the Next is that you effectively have 3 video layers. And you have the ULA, you have layer 2, and then you have the sprites. And you can configure that order of those 3 layers any way you want. Anyone can be on top, anyone can be in the middle, and anyone can be on the bottom. But you can't have like 2 ULAs and a layer 2, and like 2 layers of sprites and a ULA. It doesn't work that way. You have to have them, all 3 of them, in one order. You don't have to enable all of them. And in fact, what I'm going to be doing is enabling only layer 2. So it doesn't really matter where the sprites and the ULA are. And then you have the tile map, and the tile map sort of exists alongside the ULA. So it would take its space within that layer. And you could have that ULA layer be the tile map, or you could have them together. I'm a little fuzzy on exactly what that would look like. I haven't experimented with it yet. And then furthermore, layer 2 can be combined with a blending layer, and I was not able to find really good documentation on what that really means. So for you Next folks out there, please put down in the comments exactly like what these bullet points really look like, especially this blending layer. How does that actually work? Because I couldn't figure that out. But anyway, for my demo, there's no need for blending. There's no need for multiple layers. I just want to have one bitmap on which I can do the best possible plot of a Mandelbrot set that I can do. So for that, I've got layer 2. It lets you have, like the low-res layer, independently addressable pixels and its own palette. In fact, it has a default palette, so I don't even bother coming up with a special palette for. I'm just going to use the built-in palette. And then for layer 2, you can select one of 3 different bitmap modes. Now, there's sort of the lower impact in terms of memory. It doesn't require as much RAM to be dedicated to video if you select the 256 by 192, which is the standard resolution, and that, of course, will mix better with a ULA mode. And you can get the 256 colors, and when you're doing something where you're playing with the layers, that's probably the way to go. It just will probably blend together a lot better, and it's not going to create some weirdness that I could imagine. And of course, you're also saving on the memory. But in this case, like I said, I don't care about other layers. I just want that one layer 2 to be as good as possible. So then I have to make the choice of whether I want to have colors or resolution as the driving factor. Well, resolution doesn't buy me a whole lot. I could do 640 by 256, which is pretty high res. I mean, that's a much higher resolution than the original Spectrum. But in that mode, I only get 16 colors. So for the same amount of video RAM, I can get half of that horizontal resolution. Just do 320 by 256 and 256 colors, because that will give me the better looking plot. Rather than seeing the same colors repeat over and over again, I'm going to see just a deeper range of colors, and it just generally seems to look better to do that. And it would probably also take an extremely long amount of time to render the 640 by 256 bitmap for pretty middling results. So it was not as interesting to me. So let's actually see what it would take to do that. So I will go here into the code. And what I have is another version of the Spectrum Next Mandelbrot demo. It's just made a little bit different. You'll notice here that ahead of including the Mandelbrot 24.asm that we looked at in the last video, that I have put different bounds on there, and that's because of the 320 by 256. I really need to change up the bounds of the plot so that it's not as distorted and that it fills up the screen. We get a lot of goodness out of it. And so then we have, again, 320 by 256, and sticking with the 48 maximum iterations to match up with the 320 by 240 demo that I did for the Commander X16. So we will have more pixels, but the same number of iterations, because it seems at this resolution that 48 iterations is that point where if you do more, you start getting really severely diminished results from that you don't really get a whole lot of more information into your plot. So let's take a look then at this, the Mandelbrot 24 ASM. So we're using, again, the 24-bit fixed point. And then what you'll notice here, these are still the default values that we override over here. All of these values will override what we set up in here, and these default values, you'll notice, is the 120 by 96. It's still the default state for this library is to use the low res mode. But then one thing you'll notice here in manget is in the comments that rather than having the B and C registers hold the X and Y values, now I enabled this to have X and Y values that are bigger than 255. So I'm making them 16-bit values and using the mandx and mandy variables to do that. Of course, you can see they are both double words, but I only need a single, I only need half of that space for each of them. And then later within the code, I use these for 24-bit fixed point values. But for this, I'm just expecting them to be 16-bit integers, and then I convert them by loading that into HL, the value, and then making b 0 so that it will be that integer value 0.0, and so on. And so I not only refactored this in here, I had to then go back and refactor the low-res one, and we'll talk about how that went a bit later. But first, let's take a closer look here at how we do things with layer 2, where, again, I am starting the layer 2 at 4000 hex. So basically, I'm taking that window, that slot in the memory map, and then switching that off to a different bank that is used for layer 2. And so again, I'm using a whole bunch of these next reg instructions to set that up. So I'm saying here we're going to have layer 2 on top, and that we're going to have 256 colors, and then I'm setting up the memory banking here, so that I'm saying that that slot 2, which is that starts at that 4000 hex, is now going to point to bank 8 instead. So there's the concept of 8K banks and 16K banks. So bank 8 is the 16K bank. So that is comprised of two 8K banks, 16 and 17. So I'm mapping 16 and 17 to slots 2 and 3, and then that makes just everything line up where I have a solid 16K of memory that I can write to for this bitmap. Very simple, and let's see what else we have to do. Oh, another thing is to display layer 2, I actually have to output to a port. Instead of using NextReg, there's this port 1230B in hex. That is the port address, and if I write a 2 to that port, then it will display layer 2 for me. And that's it. It'll otherwise it works pretty much the same, with the exception that this particular resolution of layer 2, you'll notice it's Y first and then X. So it's rather than all being rendered horizontally one row at a time, it'll be rendering a column at a time, because that's how layer 2 at this resolution has its bitmap structured in RAM, which is a bit different. Most computers, of course, do it the other way, and in fact, other modes within the Next do it other ways. And then, of course, you also have that weird way that the Spectrum originally did it too, with all the interleaving rows. So yeah, whichever way you like to structure a bitmap in memory, the Next has you covered for all of them. So anyway, yeah, so we just do that, then we hit that infinite loop at the end, and now I'm calling this man5.next. This is the fifth attempt at creating a demo, and I think this is really the best possible one that you can have for the Next. So of course, I'm sure somebody could probably make one that's faster or prettier, but this is where I'm gonna sort of come to the end of the line on it. So here in Zasarix, I am going to load up man5.next, and we'll see how long this takes. And there we go. As we can see, it is rendering it out vertically. And yeah, it's, I mean, we haven't hit a lot of the high iteration stuff yet, but you can see it's going pretty quickly. I mean, not as fast as the low-res one, but we're dealing with a lot more pixels and a lot more iterations. So, here we go. And also, and another thing you notice is we're not cheating, especially here once we get to where the infinite part of the plot is much thicker, that we are calculating that top half first and then the bottom half. We're not just assuming symmetry here for this plot. we're really putting it through the paces. So I think at this point we're going to fast forward through this, and we'll come back at the end and see how long it took. Oh, here we're reaching the deepest part. These are the longest bits, and you can see it's still moving along pretty quickly. I tell you, if my old IBM PC running at 7.44 megahertz could do it this fast, I would have been thrilled. So here we go. We're coming down the stretch. All right, almost exactly 3.5 minutes. So that's pretty impressive. Let's go take a look now at how that compares with all the other times we got. So again, to recap, the Commander X16 at 320 by 240 at 48 colors took just over 12 minutes to accomplish. But with the next, as we saw last time, the low-res mode was able to do a 128 by 96 a lot faster, and with 22 colors, and using the refactored code that I had. So I reran it and retimed it, and that came out to 20 seconds. But again, that was not too not too good of a plot, and I did a similar plot with Commander X16, which still took quite a bit longer. But then now with the layer 2 plot, 320 by 256 pixels at 48 colors, so we're talking another 16 rows of pixels, and I think I also have this zoomed in a bit more, so there's going to be a lot more iterations going through there. That black middle part is quite a bit bigger in this plot, but still I was able to get it in 3.5 minutes, and so I would say that it easily makes it 4 times faster than the Commander X16 if it had to do a similar amount of calculation. So kudos to the next team. There is some very interesting graphics modes. They are not exactly simple in their approach. It is definitely complex. But it definitely warrants a closer look. And I hope that you take a closer look at it and see what some of the community for the Spectrum Next is coming up with. There's some really interesting things out there. And hopefully you'll be able to get your hands on one of the machines too. I'm hoping to get mine. So anybody wants to unload one, let me know down in the comments. I might be in the market for that. Otherwise, we're all just waiting for the last Kickstarter to be fulfilled and then the next Kickstarter to even happen. So let's hope that all that starts coming into place, especially with a lot of that supply chain issues, which unfortunately has completely stymied progress on the Commander X16. At least the Next was able to acquire a lot of their stuff in time to be able to to get at least some of their stuff into production. Hopefully it all works out. So I hope you liked this episode, and if you do, please like, comment, and subscribe here on YouTube. But if that's not quite enough for you, you can go the extra mile and join us over here on Patreon. And like the folks you're seeing right now, you could get a chance to see my videos before they go public and really get a chance to interact with me more and have a real impact on my content and see just how awesome we can make all this old retro stuff and some of this new retro stuff like this Spectrum Next. All right. So again, I hope to see you again very soon, and I hope you are staying safe and being happy and healthy. All right. Bye-bye.